Okay, so last time we kind of ended the class with the Cauchy stress equation. And so we're going to talk a little bit more about stress today. And then today should be the last lecture on stress, and then we'll move into the conservation equations. So let's start. I got to start every class by drawing a potato. So this potato, we're going to slice it, okay? And that slice will be, well, I want to say that the potato itself is oriented perfectly with, stop doing that, the principal stresses. So, when I say potato, I just mean an arbitrary body, right? The slice, the plane of the slice, is defined by a unit normal vector. And then we also have some traction vector. Emanating from that coordinate system that we placed on the slice. And so we're going to just start writing down some equations we know and see what we can do with them. Okay? So the first thing is we have Cauchy stress equation. Remember, we derived that last time. And in this coordinate system, or given what we have here, the state of stress is sigma 1, sigma 2, sigma 3, and 1, and 2, and 3. So these are the components, right? And so if we work that out, it should be obvious that that's in vector. The traction vector is a vector, sigma 1, n1, sigma 2, n2, sigma 3, n3. Okay, so now what I want to do is I want to write down the component of the traction vector in the normal direction. So I'll call that Tn, okay? So, if you wanted to take a component, a component of the traction vector in the normal direction, what's another way of saying that? Like we want the component. So the traction vector is oriented arbitrarily, right? We just some arbitrary direction. We want the component of it in the normal direction. So how do we get that? Take the dot product, right? Exactly, right? So dot product is just like a projection operator, right? A lot of times when I'm describing it to undergraduates, you can think of it like, what I mean by projection, you can think of like, if you have a vector, or I don't actually describe it in terms of vector, just if you had anything, and so you want to know what the component of that with respect to the ground is, right? If you had like sunlight up here, it's the projection, right? It's like the shadow. Like if you had a post or a tree that's leaning, right, it's the shadow on the ground, right? So that's what I mean by projection. So mathematically that means we're going to take the normal vector, the t vector, and dot it with the normal vector. And that'll give us the component of the traction vector in the normal direction, right? And our traction vector is defined over here on the right-hand side, right? So basically just dot that vector with the normal vector. And that gives us sigma 1 n1 squared plus sigma 2 n2 squared plus sigma 3 n3 squared. All right. So again, I'm just writing things down that I know, and we'll see why in a second. Okay. The magnitude of the traction vector, right? The magnitude of any vector is the sum of the squares of the components of the vector, right? And so in this case, we're basically we want to write down, or we're going to break down the traction vector into a normal component and a shear component. So a normal component is defined, and the shear component would be in the plane of of our slice, right? So TS squared plus TN squared. And, you know, I don't like, as I've already talked about in this class, I don't like to deal with square roots, right? So we're going to square both sides. Get rid of that square root sign. So then we have t squared is equal to t n squared plus ts squared. And that's equal to sigma 1 n1 squared plus sigma 2 n2 squared plus sigma 3 n3 squared. Finally, we have that the magnitude of n, because it's a unit vector, it's equal to 1, right? By definition. And so that's n1 squared plus n2 squared plus n3 squared. Oh, so n3 squared. So we have 1, 2, 3 equations with n squared in them, right? So I can distribute that squared, I have n squared, right? Yeah?
Why is Cn n1 squared?
Tn.
The first equation.
Okay, so t is this, right? So you already have an n in there, and then you're dotting it into n. So that you get the n squared. So all 3 equations have n squareds in them, right? And so we could set up then a linear system to solve for the n squareds. So I'll write that down. That would look like this. I'm just going to write down a system of equations. We'll have 1, 1, 1, sigma 1, sigma 2, sigma 3, sigma 1 squared, sigma 2 squared, sigma 3 squared times the n squareds, n1 squared, n2 squared. And that's equal to 1 Tn Ts squared plus Tn squared. All right. So we could then say, plug that into Mathematica, symbolic equation solver, right? And we could solve that for n1 squared, n2 squared, n3 squared. And we're not going to do that, but I'm just going to write down what the result would be, right? So n1 squared All right. Now, by definition, sigma 1 is greater than sigma 2 is greater than sigma 3. That's how we define them last time we talked about the principal stresses, right? So by that, like sigma 1 is always greater than sigma 2, so that first term in the denominator is going to be a positive number, right? The second term of the denominator, sigma 1 is greater than sigma 3, another positive number. You have a positive number times a positive number. Then this is going to be greater than or equal to 0. Just for observation. And I'll point that out on the other ones too. So I'm going to write down sigma n2 squared is equal to what happened? So by similar arguments, this is less than or equal to 0. This is greater than or equal to 0. So with that, we can actually set these equations. I mean, we know the equations will be greater than or equal to 0, less than or equal to 0, greater than or equal to 0. And then we can multiply out the denominators, get rid of them. And then finally, we get this equation. Tn minus 1/2 And what if I call this whole thing x squared. Call this y squared. And call this r squared. What do I have? What's that? Equation of a circle, right? Equation of a circle. So that's just for the first one, but you'll have similar equation for the other ones. I guess I'll go ahead and write them down for completeness. And I'm sorry if y'all kind of find this kind of boring. I actually find it kind of boring also. Yeah.
I think the equation for n3 squared is incorrect. The denominator should be opposite. Sigma 3 minus sigma.
I think it's sigma 1 minus sigma 3, sigma 2 minus sigma 3. No? I think that's right.
So the second one you use sigma 2 minus sigma 3, sigma 2 minus sigma 1.
Yeah, but this is sigma 1. Yeah, I think these are right.
Yeah, because inequality sign is different in the third equation. It's
Yeah, but yeah. So this is positive. This is bigger than that, and this is bigger than that. So that's positive. This is bigger than that, so that's positive, and that's smaller than that, so that's negative, and that's why.
yes.
And again,
If you
Yeah.
swap, it's still the same result.
do what?
No, like you swap them, it's still the same result. So
Well, if you don't believe me, just plug it into Mathematica and solve the equations. Because I mean, I wrote them down from
no,
just.
like
You
you
know.
swap them,
Yeah.
you get negative,
Yeah,
negative,
yeah,
which is
yeah.
positive.
Yeah.
So it's the same result.
So I'll go ahead and write down the others for completeness. I was saying, I kind of find this boring, but it's in every continuum mechanics textbook in the world. So, and there's some insight about what we can get. There's some insight gained from it that has implications for plasticity modeling later. Okay, so there's our three equations for three circles, and what that results in, so we can write down in this space of Tn, Ts, we can say that sigma 1, sigma 2, sigma 3 you have these three circles like this. This is T max. T max is just the radius of that circle, the largest circle. So that's 1/2 sigma 1 plus sigma 3. And what you'll find is, with those inequalities, is that the state of stress is always in this region. And what are these circles called? Mohr circles. And that's where I have this little thing I pulled up earlier. So this is a little animation that shows that. And this is our box that we're. And this represent. I mean, this box represents our potato. This plane represents the slice we're making through that potato, and then we have a coordinate axis there, and a traction vector, and T and TS, and then here's our three circles, and then we have different values, potential values for stress, right? And what this basically just shows is that, you know, no matter what, and then the black dot is the state of stress projected into the TNTS plane given from the full stress tensor. So, you know, again, it doesn't really matter what the values of stress are. Things will move around, but that dot will always be somewhere inside those circles, right? Doesn't matter how I change the plane, change the cut plane, the state of stress is always within those circles, right? And of course, you know, you might have already learned some very simple inelastic models, like the Mohr-Coulomb model in geomechanics, right? By basically looking at these circles and drawing a line tangent to the circle back down to the origin, and that defines like a shear plane that this, if the state of stress exceeds that, then the material would fail, right? But technically the state of stress can never be outside the circle, so it doesn't actually exceed it. It just slips along it. It just sits on it, right? So the state of stress is either inside the circle or on the surface, but it can never be outside the state of stress. So we'll revisit this. I mean, there's something more to be said in just a second, some simple examples that show, based on this, you know, like some very simple failure models, but we'll revisit some of these concepts when we talk about constitutive modeling later on. Not going to go into them, but there's also, you know, we can reduce some three-dimensional problems to 2D through assumptions we call plane stress. So I'll talk about that one just quickly first. And I'm not going to write down the equations for Mohr circles because it's just, I don't think it's that important. But let me just talk about what plane stress is. So plane stress is like if you were to have a long slender sheet under load in the plane, right? In the plane of the sheet. Basically, if you were to draw a traction vector from the free surface, right? So from the surface of the sheet, the traction is, or, you know, the traction vector is stress-free on any free surface. So I'm not talking about making a cut in an otherwise body and drawing a traction vector that would result from external forces. In this case, I'm talking about a free surface. The traction vector is the zero vector. And so basically, if you have a very long, narrow sheet, if you were to imagine looking at the cross section of stress through it, if it's a free surface here and the value is 0, and it's a free surface here and the value is 0, then, and if it's a very thin sheet, then it's kind of hard to imagine that there's going to be if it's 0 on one surface and 0 on the other, that there's going to be some enormous stress through the plane, right? Well, in this direction, I'm sorry, in the normal direction. Right? So the stress in this direction would be 0, the stress in this direction would be 0. So it's kind of hard to imagine that there's going to be some enormous stress in the center of that. And so basically, under this assumption of plane stress, we assume that the through thickness stress is 0. And then you can basically cancel out any component of the stress tensor with like, imagine this is the 3 direction, 1, 2, 3. If the normal direction is 3, then you can cancel out any stress that's in that has a 3 in it, and you can reduce the stress tensor to a 2-dimensional problem, essentially. Because the whole bottom row has 3s in it, right? 1, 3, 2, 3, 3, 3. Right? The whole last row of the stress tensor. So that's plane stress. And then there's also one called plane strain. And each of these have their own sets of Mohr circles associated with them. So plane strain is sort of a problem where you have instead of a very thin section, you have a very, very thick section. So you have a very thick cross section, and you're, say, applying a load along the axial distance, then, given that strain, if you think about it in terms of like change in length over length, well, if I'm applying a load this way, then the material will deform out of plane in some way. It will deform this way a little bit, right? But if it's very thick, then the original length is very large. So you can make the assumption that, the 3 direction, this is like, again, the 3 direction of a coordinate system, then you can make the assumption that like the 3 components, any component with a 3 in it of the strain tensor is approximately 0. Because again, if you're pulling on the bar this way, say in the 1 direction, you'll have some out of plane motion due to Poisson effect, but the strain will be small because the original length is so large. So this would be a plane strain problem. And again, so there, you can reduce some problems to 2 dimensions, some 3D problems to 2 dimensions under these assumptions, and they have their own sets of Mohr circles. And if it's of real interest to you, I can point you to some references. But any continuum mechanics book would cover it. Not so relevant to us. So let's imagine we have a sample and we're going to pull on it in basically just a 1-dimensional test, right? Long cylinder sample, we're going to pull on it. So with a traction vector y. Originally we have a coordinate system x1, x2. Anybody know why I wrote the x1 up and the x2 to the left and not x1, x2?
There's normal, along the axis.
Well, that's why I'm going to reduce this to a 1-dimensional problem only in x1 essentially. But so I wanted x1 to be along the length, but I wanted my coordinate system to be right-handed, right, out of the board. So remember from like physics when you first learned about vectors? I see professors sometimes like put a coordinate system up that's left-handed, and it always drives me crazy. because then like none of your cross product rules work. You know, like you have the opposite signs. Like please always use a right-handed coordinate system. Remember how you tell? Yeah, I always use my hand, right? So I like, if you put your hand, it's like in a sense of a cross product, right? So x1 cross x2, you should point, your thumb will be the direction of x3, and you want that to be right-handed, right? Like, if I tried to use my left hand, my thumb would be into the board, which, I mean, just, it'll be okay, but just be careful to. All right, anyway, that's just a little aside. Okay, so state of stress for this problem is just one-dimensional. Y, 0, 0, 0, 0, 0, 0, 0, 0. And what we want to do is we want to see how this, if I change a coordinate system, say to x1 prime, x2 prime, over an angle theta, then we know then what we're looking for is what is sigma prime, and we know that we can transfer, you know, we can rotate, the stress changes through a rotation via r sigma r transpose, where r is equal to cosine theta sine theta 0 minus sine theta cosine theta 0, 0, 0, 1. So that's our rotation matrix. And if you do that, if you look, then the sigma 1, 1 component is y cosine theta, and sigma 1, 2 prime is y over 2 sine theta cosine theta minus y over 2 sine 2 theta. And if you try to find the angle at which maximizes these, what you'll find out is that it's 45 degrees. So returning to our block over here, then if we rotate it, or if we had a state of stress, and we wanted to know what the maximum state of stress was, with respect to the original coordinate system, it would be along a plane that's 45 degrees. And so this is we call this a shear stress. The 1, 1, 2, 2, 3, 3 are normal stresses. Any of these are called shear stresses. And what we see is that the shear stress is as a maximum at 45 degrees. And so you can basically use this to develop a failure criteria, or what you'll find is that, and that's called the maximum shear stress criteria. And what you'll find is like brittle materials often behave like this, right? So if you have like a ceramic, or maybe a very homogeneous rock, and you were pulled on it, like put it in a test specimen and pulled on it, an MTS machine and pulled on it, then what you'd find is that often it will fail in a plane of 45 degrees like that. I don't know if you've ever observed that in lab or anything. We'll talk more about that when we get to constitutive modeling.